So today's speaker is Dr. Jason Osborne, for those of you who don't know, a faculty member here in the Department of Mathematical Sciences. And I am not going to say too much because whatever I say about what he's going to say would just be an imperfect version of what I'm sure will be a great talk. So without further ado, Dr. Osborne.
Thanks. Appreciate it. Let me get all my Zoom windows in order here. Just give me a moment to move some things around. Yeah, so this is going to be an interesting talk. I appreciate everybody's patience on this. I'm giving a talk in England next week, Thursday, and I wanted to practice it before I gave it. This would be my first talk over Zoom, so I appreciate Quinn for setting this up at the last minute and giving me the opportunity to practice this. So I've, well, in the old school, they used to call them comic books, but I guess I've written a graphic novel now. And so I think today's talk is to kind of talk about this graphic novel. It's situated around the math. It's a math graphic novel, so it's going to be a bestseller anytime. And then it's about the mathematical subject of curvature. Okay. Let's see. So the talk's going to be in a couple of parts. The first thing I want to say is I'm going to demonstrate in this talk some of the features that I did in the graphic novel. So this talk is going to be like a book. Okay, there's going to be, I'm going to set up the book with some background material. There's some background sections. And then there is I'm going to do some excerpts of the graphic novel called The Curvature Story. And then I'll kind of conclude with what I think is a pretty cool result, and then give you some time to ask questions. Okay, so yeah, those of you that know me, you know that it's hard to know when to stop. So I will try to be careful about that. Those that don't know me very well, a beginning is always the hardest thing. Starting anything is a hard thing. It's a blank white page, so beginning is hard. This talk is particularly challenging too, because I want to try to tell the story through pictures. So I have the problem of like what pictures to actually include in this talk. So we're gonna talk about this idea of curvature, and from a loose perspective, curvature is this kind of the shape change in the surface. So I like to imagine like a helicopter that's flying over some mountains. It's shining a spotlight down, and you can see the shadow on the ground, but the pink part is what's being illuminated on the surface by the spotlight above. And kind of talking about how that surface changes shape. That's the curvature idea. We want to quantify how much a surface is changing shape. Okay. I did want to set the historical perspective for this a little bit. My wife a while ago got me as an anniversary gift. This is what you give a mathematician, I guess. Einstein's 1912 manuscript on special theory of relativity. And this is a really interesting, in the preface of that book, when they're going through the history of it, they've got Einstein quoting to his friend Marcel Grossman that Einstein's going crazy. He's run into some mathematics. He's hit a wall in some of the physics that he's trying to do. He's trying to develop general relativity at this point. General relativity is 1916. So here are Einstein's handwritten notes in 1912, 4 years before relativity theory. So if you look inside of this book, I think it's kind of fun to see Einstein's handwriting. There is some new notation that he's kind of working with. And let me see right here. This is something this is a math talk, so I can use a little bit of math lingo. Many of you are familiar with a matrix. So here's Einstein using what is known at that point about matrices. But you can see it's really interesting historically that it's written in like on a kind of a cheap paper. He was in Prague at this point, writing on paper and brown ink. But Einstein gets a better job. He gets a new job in Zurich, and they got better ink there. It's in black. So you can see this black line kind of marking through what we typically call linear algebra. And Einstein needs something way beyond linear algebra to tackle what would 4 years later be the general relativity result. So he starts to look into something called the tensor theory. And here is in black ink some new ideas that he's starting to work with and develop. Okay. Now, when I say develop, he's starting to use the mathematics that was, that was in existence. Sorry about that. I think I missed a mark there. So whenever I'm feeling a little too smart and I think like I know some stuff, I just pick up this book by Ritchie Calculus by Schouten. You can see that this book was written in 54. It was originally written in 23, a couple years after Relativity. It's a geometry book, and the claim to fame is it has 16 figures in the whole book. Okay, this book is dedicated to Ritchie, and Ritchie was in 1887, 1880s. So 50 years after Einstein was trying to pick up this tensor theory. So mathematics tensor theory was kind of already known. He just needed to learn about it. And, there's some complicated looking formulas with no figures given. And then there are some new terms in that underline that Schouten kind of developed. Okay. And so here's accidentally one of those pages that has no figures on it. It is like, you don't even know what's going on here. It's just a page of formulas. And like I said, it's fun to pick up this book when I feel like I know something, and I just look at this and I realize I don't know that much at all. Okay, so tensor theory is behind relativity theory. Tensor theory is going to let us do some of this, the mathematical parts of curvature, but it's just a bear, right, to compute with. And so one thing I was thinking about preparing for this talk, I was reading a little bit about Feynman's Nobel lecture. And at the beginning there, he's talking about, he's going to use his Nobel lecture to talk about a thing that he would not be able to talk about anywhere else. He's going to talk about his path to developing quantum electrodynamics, right? He's going to tell you, he's going to show you where he ran into walls. He's going to take you on a journey. He's not going to talk about the result. He's going to talk about the story. And so this is kind of what I was thinking about with a curvature story. I've got two characters in it. They're Pete and Brenna. Brenna happens to live in Australia, and Pete coincidentally happens to live in North Carolina, halfway across the globe, or 3/4 of the way across the globe. I don't know. But Brenna goes on a journey to meet Pete. She does a sailing part the first trip, and then she does kind of her thing, and then gets over to North Carolina to meet Pete. So I'm going to do what Feynman said. I'm going to ask your indulgence. I'm going to tell a story, but there's going to be some little things around the story's edge that might not have any relevance. They're just there to kind of be entertaining and tell you a good story, I hope, which is my goal. Okay. I just wanted to set the stage for this also a little bit. This is a very short story about my life in mathematics. I've written some math papers, and you'll see an evolution here. These are some papers with my co-authors. Not a picture in sight for a while. You'll notice that. And then finally, I wrote a paper. I'm like, man, I really need to draw some pictures because I'm struggling with what's going on here. And, the pattern continues. A friend of mine did a great example in a paper, and I'm like, well, I can do an example too. So I'm going to try to write a paper about an example. And kind of anticlimactically, here is the result on the left of that paper. So I've got two particles, one catching each other, and I felt very proud of myself for getting this result. Right, but I wanted to go more than that, and I ran into some difficult mathematics and had to delve into some differential geometry books to kind of do nothing but pictures so I can understand what the heck I was computing. Okay, so that is my evolution. You can see I've gone from almost completely from formulas to almost all pictures. Okay, the book that you saw referenced there was Michael Spivak's Introduction to Differential Geometry, a comprehensive introduction, volume 2. I happened to see Professor Spivak. Oh, by the way, let me talk about the albatrosses. I mean, this is a hard subject, differential geometry. I mean, look at the names involved: Gauss, Riemann, and Cartan. I mean, these are heavy hitters in mathematics. And so I understand where Feynman's coming from, that if you're going to talk about this subject, I mean, you've got the past weight of their results hanging around your neck that you have to kind of be consistent with, okay? I happened to see Spivak at a conference. I signed my book, and I got him to sign it. I kind of was feeling fanboy that day, so I got him to sign my book. And then I felt a little bit weird about that. It looks like I've stolen Spivak's book, so I made sure I put under there, like, he signed it at the joint math meetings 2011. I got to talk to him a little bit about mathematics. I was particularly interested in how he got to write books. I mean, how do you get a job where you just get to write books? And I didn't get a good answer. He just told me about stories of his friends that were good mathematicians and they drive taxis in New York. So I don't know what I should take from that story. But so this is the backdrop for what I want to talk about today. And, you know, Feynman also had something to say. And I don't know if any of you have run into this. Your family or your parents or your friends, they hear you're a mathematician and they want you to tell what it's all about. Like, what are you working on? And then what Feynman is saying here is that we do the wrong thing as scientists. We jump to the coolest thing that we can think about, and people don't have the background to understand what the heck you're talking about, okay? And recently, this is all going to tie together, I promise, that recently there was the discovery of the first image of a black hole. And I was thinking as a teacher, like, I'm sure people are going to think that's a really cool result, right? What if a student says, man, I really like that. I love the pictures, but how do I get involved and learn what the heck is going on, right? So we really need, when we're talking about our subjects, really need to sometimes take a big step back and talk about the things that have gone on before. And this is my attempt at showing you what has gone on before the first image of a black hole. Okay. Now, I promise that this is all going to tie together. I got thinking about curvature, and one way I could go about that is here's a Google map. You know, we have got a lot of technology nowadays. I'm zooming in on Iowa, somewhere in the middle of Iowa, and you'll start to see a 1 kilometer by 1 kilometer square. It takes a while to zoom in on that. Right? And the question is, like, what is the area of that 1 kilometer square, right? At the same time as I was doing this talk, I was also reading this book by Walter Miller. It's called Canticle for Leibowitz. I'm not sure if anybody's read it. It's from 1959. Seems like the rage now is to write post-apocalyptic books. Well, in 1959, Walter Miller wrote one. Some sort of apocalyptic event happens. A lot of information goes underground. Monks are trying to preserve knowledge and stuff. And the point of this is I really got thinking in that book, what if you'd completely forgotten the context for everything? For example, like these characters, there's a scientist coming back into its own. There is a character that is kind of smart. They come across, the book author doesn't say, but they've come across some of Einstein's notes. There's this weird tensor notation. The author is not talking about that, but they're talking about tensors. And the character is not sure if it's a hoax, right? If what they're seeing, what the heck it is. If it is true, it seems brilliant, but you know, there's no context, right? So this is what I wanted to really think about. I was putting myself in this talk in the perspective of, you know, I kind of know something, but let me challenge myself to think about it differently. So, I mean, some people believe maybe the Earth is flat. I'm not going to go that far. I'm going to say that I think the Earth is seemingly flat. Okay. So in a curvature story, our characters are going to kind of learn about the consequences of living on a sphere. Okay. So imagine with me that you forgot a lot of information, right? You may not know the context for it. And I got thinking, well, if some event like that happened, clearly Google would still be around, right? So here's Google, right? Google, I'm looking at a 1 kilometer square near the equator. And Google has this ability to do some computations in Google Earth. And it's kind of interesting that the Google Earth says that a 1 kilometer square drawn near the equator is about a 1 kilometer squared, or 1,000,000 kilometers squared, plus about 5,000 square meters. That's what Google, the internet, was saying. Now, I have no context if that is right or not. Like, how would you determine the rightness of that? So, you know, I started, you know, myself to go back through that knowledge. And I'm like, well, what would I do? I would try to draw a square on a smaller sphere, because a sphere the size of the radius would not be able to fit on this page. And it takes a while to zoom in on it, even if it did. So I was looking at this 1 kilometer square and noticed that, you know, if I increase the radius of the sphere, the area is a number bigger than 1, right? So here, the shape of the sphere is what is causing the area to be bigger than you might expect, okay? Now I thought maybe 1 by 1 is a wrong number to go with. Let's try a 3 by 4 rectangle on a sphere of radius about 3 in this case. And you'll see that the answer is going to be bigger than 12. It's around 13. And then as the sphere radius increases, the area starts to get a little smaller and smaller. So for those of you in Calc 1, this is a great example to ask your professor about a limit, right? This is the limit. We're letting the sphere radius get bigger and bigger, okay? Now this is just for flavor, the mathematics over here on the right, and to kind of set what I was trying to do in a curvature story, okay? This is what you might see in a textbook, a bunch of formulas. You would see a formula that's about, and then here's a picture. I just think how much cooler it is if you just push a button and you get to see some of these formulas change numbers. You get to see this 1 kilometer square change area based completely on its latitude, right? So this is my take on, I've forgotten everything. I don't know if 5,000 meters squared is actually the right answer. Is that too big? Did Google Earth get the calculations wrong? I really don't have any idea. I'll leave it out for you to show what does the math actually say, okay? I had to shorten this talk, and that was one of the things that went, my justification for that. So, you know, as I've been kind of trying to allude to, curvature can be very mathematical, right? This is a take, I've written some Maple code that feeds to Mathematica, that feeds to drawing these pictures. These pictures I can use to draw some moving pictures on a surface. And I just really want to call your attention right here to this normal vector, the vector n that is pointing straight up. That is going to be the key to computing curvature from kind of an intuitive point of view. Okay, so I'd like to tell you what curvature is without talking about how to compute it, how to get stuck in all the depths of this mathematics here, tensor language or whatever. Okay, so here we are. Remember, it's post-apocalyptic. The only thing still standing is Google. So I'm able to do a Google search for corrugated stainless steel, right? Stainless steel, corrugated. I don't know. I had the reason to have to cut some of this recently. It's hard as hell to cut that stuff because of these ridges that are cut into it. So what I want you to be seeing here is I created a mathematical function for this corrugated steel. It's a little zoomed in part. Now watch what's happening. I'm looking at a illuminated portion of the stainless steel. I've got these normal vectors around that boundary, the edge of that region, and I'm then created this sphere, or Gauss created this sphere to be correct. And I'm looking at these arrows for the normal vector on the sphere itself. And the goal is to look at the area on the sphere divided by the area on the surface. The snappy way to say what curvature is it is how much the normal vectors are changing, which is computed by the area on the sphere, how much the normal vectors are changing over a given amount of area, okay? And then if you notice that the area region is getting smaller and smaller in the limit, so there's ask your Calc 1 professor or 2 or 3, there's a limit involved again. And my claim is that because there's no area on the sphere, the curvature of the corrugated steel is equal to 0. You intuitively understand what that means. That corrugated steel was probably made by somebody from a single sheet of steel, and it was just that pattern was just pressed into it, right? So the corrugated steel, because it changed shape, the structure of it changed, it stayed flat, it stayed curved, but in one of the directions it's bent, but the total curvature is 0, curvature at that point. But because it's bent in one direction, that gives it some strength. How does the corrugated steel link to the sphere? Noah, this is just an example that the sphere I'm setting up that if you want to talk about curvature without resorting to some computations, we say, I want to start with a 0 curvature surface. So what we're going to find on the next page or two is that on the sphere will have non-zero curvature. You're actually going to see what that's going to look like. So when the surface is flat, we're not seeing any area created on this sphere. So therefore 0 divided by the area of the surface is always 0. Okay. Now contrast that with a non-zero surface, right? Like the tip of this ballpoint pen or whatever. Here are the normal vectors on the left. There's an area of the surface, and I move the normal vectors to the sphere. And now you can see that there is, in fact, an area created. So the area on the sphere divided by the area of the region should limit on what is called the curvature value. Okay. Now, it's at this point I want to remind everybody that I'm supposed to be talking about a graphic novel. There's supposed to be characters in that graphic novel, and my characters have conversations like this in the book where they try to feed off of each other. You'll find in the book that Pete and Brenna go to North Carolina to a university, hint, hint, wink, wink, to learn about curvature. And they get these, if you've ever been a student, you get indecipherable notes from your professors, and it's your job to figure them out, right? So the characters are getting these notes, and they're just trying to understand what the heck they're reading, okay? Now we're into the excerpts of the curvature story itself, okay? There is a long timeline of results here. Starts back in the 1700s with Euler, goes to 1776. I think that was a big year in America, 1776. There were mathematicians in France doing math at that time. And then there's a long result of a long body of results, okay? One of the results I want to point to is, let's start simple, which is what Euler did. You can see here on the left that we've got this curve, and at a certain point we're trying to draw these circles at a point on this curve, right? If you were to look at that circle that fits the curve, right? I'm sorry, my mouse will not let me draw this very well, but you'll get the idea in a second. There's a circle, measure its radius of that circle. 1 over the radius is the curvature of that curve at that point. So here we can see that because this is a pretty simple helix problem, the circle is not changing its radius at any point. The circle that's fitting the curve is always the same radius. That is different from this tightening spiral. You can see that the radius of the circle is getting smaller, and therefore 1 over a small radius is a big number. The curvature of this curve is actually the curvature is increasing because the radius is getting smaller. Okay. Now, how do you extend these circle results to surfaces? Well, that is, perhaps where the next result, 1776, comes in, right? And, to set up that result, I thought it would be, these ideas are pretty complicated without some pictures. One of the cool ideas from 1776 is, right, there is some circles, there's the direction vector for the circle, and then there's the direction vector for the normal vector, and we need to find the angle between those. That is a hard idea to convey unless perhaps one has a picture, and then it's easy to convey, right? Done, I'm moving on, okay? 1776, we need this certain angle, and that allowed Meusner and Euler's results for the curvature of curves to kind of help them when it came to curvature of surfaces. Now, one of the ideas and the premise of a curvature story is that, right, I would like, if possible, to introduce visually the definitions that are involved, right? So here, whoops, sorry, I meant to annotate that. So here is a curve, here is a circle, right? I'm going to find the curvature of that curve, measuring its radius, right? 1 over the radius is the curvature. So I can find the curvature of the curve in this direction at that point, right? Now, this direction is a very special direction. This is a principal direction. This is the direction of smallest curvature at that point in that given direction. There is another circle, another principal direction. I can find this circle, measure its radius. And it turns out that using curves, we can talk about the curvature at a point by multiplying two curvature of curves together. Okay, so there is the result. Okay, up to 1776. So, you don't need to take this picture all in at the moment, but it's there for you the reader to peruse. And they might say, I'm not interested in this page, I'm just going to move to the next one. So that's what we'll do. Okay. Now, I'm not implying that there's not mathematics in in the book, I am just saying that the mathematics is not front and center. Okay, I've got visuals on the front, and then the mathematics for the reader that's interested, if they want it, they can kind of glance in the background and try to figure out what's going on. Okay, and here, Noah, is the answer to your question. Using the results that we develop in the curvature story, the curvature of a sphere is 1 over the radius squared. Okay, and that's why we saw that earlier, that as the radius of the sphere increased, the area of the 1 by 1 square got smaller and smaller and smaller, and it was approaching 1, right? But the fact that the area of a sphere, of a 1 by 1 square on the sphere, is not 1 is a measure of the fact that the curvature of a sphere is not equal to 0. Curvature of a sphere is just not, the sphere is not flat in the same way that the corrugated steel was. Okay. Now, here is, I'll share, spoiler alert coming ahead. No, so let's see if we can talk about that. What you end up finding is that in the curvature story is that Pete and Brenna, they come to America, they meet the professor, he gives them these indecipherable notes, and they have to go on a road trip they don't have time to understand the notes in North Carolina, so they go on a road trip. And what we're actually seeing, the pictures of the book, you are reading their notes, right? The students are writing the notes, and that is what the book comprises. Okay, so it's a little spoiler in case you were wondering what you were reading. Okay, so we're reading the characters' notes themselves. Okay, and we'll see this come full circle in a little bit. Now, I've been a student in the past, and I'm sure a lot of people have been students or are currently students. At some point, everybody hits a wall, right? You hit a mathematical wall. There are results that you just like, no matter, somebody's written it down, fine, it's written down. You don't understand it. Everybody's been there, right? So this is what happens to Pete and Brenna also. We get to around 1854, Riemann, right? And that's just a step too far mathematically for our characters, right? Because, speaking as me, the writer of the book, right? It's hard to talk about that tensor stuff in terms of pictures. I mean, I'm attempting it in the next book, but I won't talk about that here. So here we have our historical tiebacks. Remember, Einstein was 1912, that picture I showed you, right? That book. 1916 is a big year for general relativity. He needed this curvature idea and to describe gravity. But look at what happened before. Riemann laid some of the groundworks for the Riemann curvature tensor. The notation starts to come around, tensor theory, in 1869. Ritchie, the person who was attributed in that book that I told you about earlier, around 1900, they wrote that. And isn't that just in the nick of time historically for 12 years later for Einstein's friend to tell him about this mathematics that could help him with his physics problem, right? I think that's just very convenient historically, okay? Now, oh, sorry, is there a question? Oh, okay. I promise there'll be time for questions. It looks like I'm on a good clip. So if there's a question, I can definitely take it at the end, sorry. Now, I'm part physicist. I'm what you call a mathematical physicist. It's kind of like a unicorn on the top and like, I don't know, a bird on the bottom. I don't know what it is. A mathematical physicist is usually a weird kind of entity. So one of the things we saw from the Euler result is that circles became very an interesting method to find the curvature of a curve and the curvature of a surface. That was Euler's approach. So I thought it became really important to say, well, why is the curvature of a circle 1 over its radius, right? And I thought the best way to do that, especially in the context of Einstein's work with curvature and gravity, was to put that in context of, have our characters run a race. So there's some pages in the book where they start doing experiments where they're running around a track. And it's this physics result that pretty easily and quickly gets us to the curvature of a circle is 1 over its radius. Okay, so these are ideas that are developed in the book more. There's some more physicsy graphs and and stuff like that. The characters talk about, well, what if one of them runs faster? What if them accelerates? There's some pages in the book about that, and how that would that change the curvature result? Is the curvature of a circle, if they run around faster, still 1 over its radius? And I'll leave that to you if you're interested to check out the book. Okay. Now, at some point, right, we're going to kind of go backward in time a little bit. I wanted to set the context for these results, right? Thinking back to that Leibowitz book, I was really interested in this, putting myself in the headspace of like, what do you mean a person could read a thing and not know if it's true or false, right? Things that it's hard to ascertain truthness or falseness if there's no context. So the context, I was trying to put these curvature results in the context of maps. This is where geometry developed from. It developed from map making. Map making has been around since 1492 probably, or 1500s or something, right? So people have been working on the map problem for a long time. And so I wanted the characters, so here's where the character development comes from. Pete has been drawing maps since he's a little kid. When he's a little kid, he's drawing maps to the candy store, okay? As he gets bigger, he gets to draw maps on computers. It turns out that Pete's pretty interested in computers, okay? Brenna's quite different. She's kind of a spitfire. She's been drawing treasure maps since she was a little kid. So, and her maps get more complicated. She goes on longer adventures, but both of them have different personalities and skill sets. Brenna's really into mathematics. So there's in my opinion, a really interesting playoff between the characters, about Pete likes to do stuff on a computer, but Brenna reins him in when, right, it helps him understand whether or not his computer code is actually spitting out numbers that actually have any relevance, So there we have that little character development. And I also in the book tried to make this a journey like Feynman was doing. Feynman didn't say, here's the straight line how I got to quantum electrodynamics, right? He told you that where he got stuck. He thought that was an informative thing, right? And so I kind of took the same tact. My characters, because they're early in their development, early on in the book, they know the distance formula with Pythagorean theorem and they misapply it, right? So they're computing differences between this point and this point. They do that incorrectly. They do that with a straight line distance, and they should be using some sort of other type of distance computation, okay? So, the characters may have some room for growth to kind of learn as they go along. And, like I said, there's a playoff between the characters. Pete starts to run some computations with his computer, happens to be called TARDIS, if anybody is a Doctor Who fan. That's the name of his computer. Run some computer code. And again, I'm not shy or the characters aren't shy about showing you what they're doing. I don't think we need to hide the mathematics. We need to make it there if people like want to delve deeper, right? There should be multiple ways to work through a book, right? But here are the visual images. You can see that here that I won't go through the details, but Pete his computer is drawing all these maps. This is Mathematica, by the way. That's what he's using, not me. That's what he's using. And finally, I was trying to end the journey here, I guess you could say. And by the end of the journey, they resolve their distance computation errors. They figure out that when you're drawing a map between 2 points that are on the sphere, and when you make a map, which is some sort of projection of Australia perhaps onto a plane, what they're seeing is some sort of distance distortion, right? And so the distance in the map is different than the distance on the sphere itself, right? And we just use basic trigonometry there. We use the S is equal to R theta, the radius of a sphere times the angle. And that's about all the technical stuff that Pete and Brenner are doing there. But the pictures help show maybe that the radius is changing. And since the radius changed here between the points in the map in Australia, the distance is going to be more. All right. And why is there a distance distortion? it goes back to the idea that the sphere has a curvature, and you're not going to get a perfect representation of distances at that point. You can't like flatten a non-flat thing. Okay, so this leads us up to kind of, you know, what I just think is a fantastic result. I don't pretend to understand everything about it, but there was a talk I heard. You can Google search the Smithsonian Channel Event Horizon Telescope, Seeing the Unseeable. If you Google that, it will take you to a talk by one of the chief, the principal investigators for that group, which happens to be a group of over 200 scientists around the world collaborating to get this first image of a black hole. Okay, now that result is at least 250 years in the making. Okay, you know, first we needed Einstein to come up with his gravity and curvature being related. We needed Schwarzschild to solve some equations to show how what the radius of that, or to predict that a black hole is even a thing. You then need to know maybe the size of that. Why is this not playing? Okay, there we go. And here's the image that they showed in that talk. I just thought, I mean, if that's not cool, I don't know what is, right? Just this cool. They're zooming in and zooming in on a black hole, and they're trying to get the image that they eventually developed. Okay. The story I've shown you today is quite a bit shorter in its history. It only took me 2 years to write this graphic novel, so that's not bad compared to 250 years, I guess. Okay, so there we have it. I've kind of got a complete, you know, there's some history I've left out between the 100 years from Einstein to the black hole image, but that would take us too far afield. Okay. So there we have it. If you're, I have a couple more slides after this, but if you're interested in, here's the back flap, the little blurb on the back of the book. If you're interested in the book, you can get it on Apple Books, and yeah, it's $6.99. Not bad. A little bit more than Starbucks coffee, maybe, depending on your drink, I guess. So I know some of you are probably thinking, and I would be similar, right, that, you know, I am not a graphic novel fan. I did not grow up on Marvel or DC. I did not care about that kind of thing. So, you know, I personally have written this, but I'm not sure it's the method that I would learn best, right? I think I just would rather read a thing. So at the end of the book, I have actually shown you what Pete and Brenna were actually reading. They were reading the professor's notes. So here are the professor's notes, right? And Pete and Brenna have distilled these notes into all the images that you've read in the book, okay? The professor, in this case, I guess it's me, spoiler alert, sorry about that, has kind of outlined the historical development of where the Gauss curvature comes from. This is perhaps what Pete and Brenna read, and they said, I don't understand anything about that. So they undertook their journey as we've just kind of outlined in this talk, okay? I'm doing okay on time. So that's kind of the end of the curvature story. I did want to kind of say a little bit about a little bit more of motivations behind this book, how I organized it, how I'm thinking about books in the future, I guess. I guess one of the things I just want to say is I think a lot of books are ugly. I mean, they just don't look good. The figures seem to be thrown as an afterthought. The font is just crap, right? The organization does not seem to work, right? For me sometimes. And I'm sure students might say the same thing. I don't even know if some students read the books that we offer them, right? So one of the books that I read, and I read very kind of intently, and is this book from '77 called A Pattern Language. It's a print book, text, right? Like, sorry, you got to thumb through it, you know, which is not a bad thing. Noah and I agree on books, thumbing through them. But this book laid out what they call a pattern language, which is basically just a fancy way of saying ideas, core fundamental ideas. Those are the patterns. So we could have a whole separate discussion on what we think are the patterns in mathematics. Do you think a limit is a pattern? Is that such a core fundamental idea that it should be a pattern, right? The integral, the derivative, right? What are the patterns, okay? If you're reading a book, the patterns are probably the characters in the book, right? Now, the language part of a pattern language is not the characters themselves. Like a book with just characters would be boring. What you care about is the dynamics between those characters. You know, what, how they're related to the other characters. And then, you know, if you're reading a book, you have to, one page follows the next. You are forced to write a book in a linear sequence. But this book that I've written for a pattern language, based on the pattern language, got me thinking about, well, how should we organize a book? And so I've organized as a book that you can hyperlink, you know, and you can see where you are in the story. There actually is a story developing. And, you know, the links are, right, a way that you move around. So I don't expect a student to read this book, right? I may expect them to go through it once, go back to the beginning, or maybe linger on a page for a little bit. That's to be expected. And that is okay, because I believe that books, it's a challenge to think about what that would look like. But books are, unlike our math books, which seem to be very linear in sequence. This book that I like, for example, here are some patterns that went into what a sub story of the book was about. What are the patterns that make a good house, a good building? Eric's wife knows about this. I think she has this book on her bookshelf at her house, right? I believe, if I'm remembering correctly. So here, like, if you're going to make a house needs to have, like, these authors believe that a house, what is fundamental, a pattern, like something that makes a good house. I mean, you need, I'm going to highlight just a couple, like light. I mean, the word light comes in so many different times. Indoor sunlight, right? A house without light might not feel very homey, right? So one thing that I'm trying to show here is I wrote some Mathematica code to figure out how all of these ideas were related to each other. I was curious if any one of these patterns was more important than the other. So I picked, like, I don't know, 50 chapters from that book. And if you look at it, the graph of that book, it's a network. These ideas are very strangely connected. They're very connected, right? And so you should be able to move anywhere through that book. I was curious about, in the pattern, in the curvature story, how I could make it so people could move around in the book at their own pace. This is still an idea that is percolating in my mind, but this is an idea that I might have. So we arrive at my last slide. I need to give Bill Cook a shout out. Let me go back for 1 second. Sorry, Bill Cook, I didn't mean to leave you out, and James here. Another plug for mathematical physicists. In the professor's notes, if you were wondering how I actually computed, how Pete and his computer calculated areas on that sphere, it was an interesting application of Stoke's theorem. So one of the footnotes in the professor's notes is the history of Stoke's theorem and how we use that result. And I'd like to thank Bill Cook and his brother James for giving me the correct vector field that I could use Stoke's theorem to compute the area on this sphere. So sorry about that, Bill. I almost left out the most important part, which was some of the mathematics. I got thinking about the math again, because in the notices of the AMS, and what year was this? I think I can't remember the number. It's volume 56, number 2, right? There is a book an article by Freeman Dyson about mathematicians kind of break up into 2 very broad categories. They call, Freeman Dyson calls them birds and frogs. And he talks about those, birds are the mathematicians that can fly at 30,000 feet. They see how all the mathematical results might be connected to each other. And then there's the frogs, who you might think are kind of ugly, but here's not what's the word I'm looking for? A pretty frog. It's this is what makes a lot of people go to Costa Rica to see this frog. But you think frogs are ugly and whatever, but they're down in the mud, so that doesn't seem that pretty. But they're down in the weeds. They're seeing all the cool details of a problem, right? And if I'm going to categorize myself here, I'm going to say I believe I'm probably a frog. Okay. But if you're neither one of those, that is okay, because there are other ways to get around. You don't have to fly. You don't have to rivet around. You can be this snake, which I'll just let you watch this for a second, because I think this is pretty freaking cool. This is a snake. It's supposed to be on the ground, but this is how curvature comes into play. Look at the snake kind of shifting its tail around, right? It's changing its shape so that essentially it turns into a frisbee. And so I don't know, is this a snake or is this a bird? I don't know. Whatever it is, it's not going to be hungry in a moment, because it's going to eat that little lizard. Okay. So if I can just give a plug for some mathematics again, and kind of, bring in some mathematics. Here is that formula from very earlier. There's a lot of mathematics behind curvature. Like I said, when I pick up scouting every once in a while, I'm always amazed about what I'm going to see. Personally, I'm really interested in these terms of the curvature tensor, extending what curvature is, and using this curvature to discuss a control theory problem, which is how could you change your shape to achieve something that wouldn't have been achievable before. So this snake, because it can change its shape, can do a thing that other snakes cannot do, which is fly. And if that creeps you out, a snake flying, then you would be with my wife on that. She did not think I should put this picture in here, but I thought it was kind of cool. And just a plug for one of my colleagues, his PhD dissertation was exactly on snakes and the geometry behind snakes and motion. And so mathematicians do study that thing. And that is the end of today's story. And I pretty much finished kind of where I thought I was going to. So at 50 minutes. So I think I'm at the end, and I will open the floor to any questions if you have them.
All right, great. Thanks, Jason. So if anyone has any questions, you're welcome to just unmute and ask them. If you'd like to ask them in the chat, I can keep an eye on the chat and I can just ask them, but we'll happily take any questions now.
I was laughing at Alan's, if Alan has written a book, he's written code to write a book also. So he's saying that he's welcoming to the Font and Graph Snob Club. So yeah, can I get my trophy at the end of this, Alan? I really want to see what that, please don't make it a Helvetica A, but whatever. Okay, I'll take any questions if you have them. So whenever I get silence like this, I usually tell my students, like, either A, I've done a fantastic job, or B, I've done the worst job ever and nobody has any questions. So it's one of those extremes. Hey, Eric, yeah.
I have a question, Jason.
Yeah.
This is the first math I've seen explained using this graphic novel approach. And I wonder, it seems like there are opportunities here that no one else has sort of gotten into for using this approach for explaining a lot of math. So calculus or other areas that might engage more different students and get more people involved.
Yeah.
Have you thought about doing that?
It's probably about all I think about, Eric. Yeah, I think about that a lot, especially when I look at all the books that we end up using, and I'm like, this could be so much better and so much more engaging. And Noah and I talk about stories all the time, like, what story are we telling in calculus? Yeah. So if, I have, I can answer this in so many ways, but, Kevin Shirley and Jeff Nicely, Kevin Shirley, Professor Shirley's in our department. He's written a fantastic calculus book. Right? Fantastic. The copy is excellent. I would use that book in a heartbeat. So personally, the way I see somebody like myself coming in is just, I'd like to add the visual layer on top of their text, right? I view books now as multi-layered. right? I view like the copy layer on the bottom. You can sell the copy layer. I view the image layer on the top. I view the outline layer on top of that. And you might be able to monetize each of those different layers separately. So yeah, I should say that there are some books that they are called that they're my friend Renee was telling me about. Oh, this sounds like, back in the day there were these books called Introducing is what they were called, and they were introducing Marxism or introducing relativity. So you can find those on Apple Books also, and they were kind of like words mixed with some still pictures. But I kind of believe I've gone the next step, and we have digital books, but they're just crap, right? Everything seems like hacked together. I believe we should do better, right, to bring the text and the images together. And I know why it's not done is because it takes 2 years to write 99 pages, right? So maybe that's why. I don't know, but yeah, I think a lot about this, Eric, and so it's things that I'm exploring, these kind of ideas. Yeah. That was a long-winded answer, sorry. A friend of mine who wrote a novel, she's been sending me all this stuff about how to get an agent and how to write a query letter and all that stuff. So that's some of the next things I'm going to do, is to try to, is this a math book? Is this a comic book? Is this a graphic novel? Seems like different agents all have different skill sets, so you got to find the right one. But yeah, I think about this a lot, Eric. Thanks.
All right, any other questions?
I guess I have one. So who do you think, with that in mind, would be the audience of this book, or does it have several different audiences depending on what layer they're going to look at?
Yeah, I know that's let me answer that in a certain way. Some of people in here of this audience may be of a particular age where National Geographic was a thing. I think it's still a thing. But, every month you got National Geographic articles. I was looking at those growing up. My parents got these National Geographic books, one that was just on the universe. As a kid, I was looking at those and all these maps. I'm like, I have no idea what the copy is saying, but the pictures sure are really cool, right? And so what I imagine is a book that's made for multiple audiences, right? People can scan through this graphic novel, and if you just want to look at the images, these ideas might seed in your mind. But then what I really dislike about some of our popular science documentaries and stuff is they take you to the other extreme. They say like, well, here's the idea from 30,000 feet, and then you have no way to get down into the details. So my hope with this book is, and books like it in the future, would be that you could look at it when you're 10 or 12 or 15. You could look at it with a high school knowledge, and you might see one thing. You could go take a college class on calculus. You might see another thing. So a book that, I hesitate to say that, people are going to look at this book for years and years and years, because I'm not sure I believe that. But I believe we should strive to write books that you might want to revisit them every once in a while, right? And in fact, that's what happened, with this, where did that, I just wanted to point out one thing real quick, because this kind of sets the stage for, sorry about that. I should have had a link directly to right here, right? The introduction to this book, this book was written in 1959, but in the introduction to this book, I'm sorry, I don't know what Mary Doria Russell wrote, but I think she's probably a famous author herself. She articulated in the introduction to that book that she read it once when she was in her 20s. She read it again later in life, and you learn different things at different stages in your life. So that's the way I view these books, that there should be something for everybody at whatever stage you're at. And that's my hope. Sorry, that was a long-winded answer, Noah, but I appreciate the chance to say something like that. Thanks.
So we are almost at 4 o'clock. So I'm sure Dr. Osborne would be glad to stick around if there are those of you who have some last minute questions. Although I am just going to briefly take away his screen sharing just to pop up here. Here's the colloquium or the flyer for next week's colloquium. So if you're interested, there's a little bit of information about next week's colloquium. Thank you all for attending, and we hope to see you next week.
Yeah, thanks again, Quinn, for setting this up. I really appreciate it. And thank you all for coming on Friday afternoon. I'll hang about a bit if anybody has any questions. I got some time.
Are the colloquiums going to be archived anywhere so we can watch them again later?
Yeah, so I will actually, I'm recording all of these, which reminds me that I should actually probably stop recording this one. And they will be put up on the department's YouTube channel. I'll be sure to send a link to that in the next announcement. So
Okay.
you should have a link to the YouTube site, and you can find them all there.
Okay, thank you.
Thanks to all the students that came. I appreciate it because you're kind of the audience. So any feedback you want to give me, it would be really useful, you know. Hey, William, how you doing, man?
Making a surprise visit.
Yeah, man. It looks like you're in a swanky library. I like that.
That's my bedroom.
Oh, is it?
It's
Yeah.
better than showing my bed.
Yeah.